Given only the chemical formula of a polyatomic ion, how will you determine the electronic geometry, molecular geometry, hybridization of the central atom, formal charges of each atoms? So in this video, I'll be showing to you some very convenient steps to follow. So let us start by writing down the Lewis dot structure for each elements in this ion. So let's start with iodine with 7 valence electrons. I'm writing down 2 oxygens with 6 valence electrons, and let us not forget that this is an ion with an extra negative charge. We can represent that extra negative charge or electron with a dot. This extra electron will be attached to a particular element here. It could be iodine or oxygen, but to help us decide which atom that electron will be attached to, we can use the information about the electronegativity of each elements. So for iodine, its electronegativity is 2.5. For oxygen, its electronegativity is 3.5. So electronegativity is a scale. It tells us that in a molecule or in an ion, the element with a higher electronegativity tends to attract the negative charge to itself, or the electron to itself. So we will place it probably in this oxygen. As you can see, now we have 7 here due to the extra negative charge. The next step, to draw the structure of the ion, we need to decide which of these 3 atoms will be the central atom. In most examples, the information about electronegativity can help us guess which atom is more suitable to be a central atom. So here, the element with the lower electronegativity, so I'll write it down here, the element with the lower electronegativity tends to share more of its electron to the other element with a higher electronegativity. Okay, so that means iodine is much more suitable to be the central atom here. Let's not forget the extra electron. Okay. Now, after determining the central atom, let us now connect electrons to form bonds, and keep this in mind that oxygen will strictly follow the octet rule. So here, our goal is for oxygen to have 8 electrons it owns plus shared with it. Also for this oxygen. Okay. Now, this one has 7, so it will share with iodine, and inside this encircled region you can see 8 electrons associated with this oxygen. For the second oxygen, you see 6. It will need to borrow 2, so a double bond is necessary. Okay, so inside this encircled region is 8 electrons. Meanwhile, for iodine, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, it is capable of expanding its valence shell. Okay. A simple explanation why oxygen strictly follows the octet rule is because the last electrons, or the valence electrons of oxygen, are located in the second energy level. So N means the second shell, second energy level. And those electrons have access to the s and p orbitals. The total number of electrons that can be placed here in the second energy level, having access to s and the p orbitals, is 8. Meanwhile, for iodine, its last electrons are placed in the 5th energy level. As you can see here, 5th energy level. The 5th energy level has access to the following orbitals: s, p, d, and f. And if it is necessary for iodine to form multiple bonds, then it can use some of the vacant d orbitals. So I will show to you how it looks like later. Now we can move on to the next step. I will just rewrite the structure here at the top right corner. Okay, now we move on to the next step, which is we count the number of electron groups, because the number of electron groups along with the structure that we draw here, can help us determine both the electronic geometry and molecular geometry. So for electron groups, you need to consider three things: the number of single bonds, number of double bonds, and number of lone pairs. Now let's look at our structure again, and we count the number of single bonds, double bonds, lone pairs connected to our central atom, which is iodine. So number of single bonds, 1. Number of double bonds, 1. Number of lone pairs, 2. And you add up everything, and the total is 4 electron groups. These electron groups will repel each other and will assume a particular configuration in space in order to minimize that repulsion. That is called the valence shell electron pair repulsion theory, and this concept gives you the possible geometries of molecules and ions. In your chemistry textbooks, you might encounter tables like this that gives you the possible electronic geometry depending on the number of electron groups in your structure, in your molecule or polyatomic ion, and also depending on the number of lone pairs, you can determine the molecular geometry. So for our structure for iodite, we encountered 4 electron groups. So for 4 electron groups, the arrangement of electron groups will assume a tetrahedral arrangement. So we can say that this is iodine at the center. You have a lone pair here, a lone pair, double bond with 1 oxygen, single bond with 1 oxygen. Definitely the separation of electron groups for our example iodite won't be equal to the ideal value, which is 109.5 degrees. Again, we have 2 lone pairs, so we can look at the molecular geometry that iodite will assume, and here it is going to be angular. Okay, so molecular geometry doesn't consider the lone pairs. It only considers the arrangement of atoms present in the polyatomic ion or molecule. So here iodine is our central atom. There's an oxygen here which forms a single bond with iodine, and then another oxygen which forms a double bond with iodine. And then if you look at the geometry, you can say it's angular. Our electronic geometry is tetrahedral and our molecular geometry is angular. Now we can move on to the next topic, which is hybridization. And in order to explain the process here, I will draw the orbital notation for each atoms. This is the orbital notation for the 3 atoms, and just take note that for the first oxygen we added an extra electron, so that's why it's 2p5. So normally it's 1s2, 2s2, and 2p4. Here 1s2, 2s2, 2p4. For iodine, the valence electrons are in 5s2, 5p5. Now, just a disclaimer regarding this discussion. This is just an attempt to apply textbook procedures in order to explain how bonding occurs in this anion for iodite. Okay, this is an attempt to use textbook procedures once again, and the reason why I'm saying that is because the most reliable information would be experiments, would be experimental data. Okay, so to guide you when it comes to dealing with hybridization is to keep in mind the following concepts. First is that an element will need to prepare in a molecule or a polyatomic ion. An atom will have to prepare the same number of half-filled orbitals as the number of other atoms it will bond to. That means for oxygen number 1, it only needs 1 half-filled orbital because it is only bonded to 1 atom. For oxygen number 2, it needs only one half-filled orbital because it will bond to just one atom. But for iodine, it needs to prepare two half-filled orbitals because it is bonded to two oxygens. Okay. Now that means for our central atom, iodine, it will need to prepare two half-filled orbitals. The problem here, as you can see, is that iodine only has one half-filled orbital. As I mentioned earlier, if it is necessary for iodine to form multiple bonds, and for other central atoms that can expand its valence shell, it will use up the vacant orbitals. Okay, 5d0. So here, in order to prepare two half-filled orbitals to bond with oxygen number 1 and oxygen number 2, we can move this electron here. It will look like this, and I might as well remove the numbers in order to avoid confusion. Now iodine has enough number of half-filled orbitals to bond with oxygen number 1 and oxygen number 2. The next concepts are actually these two go hand in hand. First is that bonding occurs through the overlapping of orbitals, and also to assume, for iodine to assume a tetrahedral geometry, electronic geometry, it will need to prepare equivalent orbitals. So these two go hand in hand, but to make it less confusing, I will first illustrate overlapping of orbitals. So here, let's say iodine will bond with the first oxygen through the overlap of these two orbitals. Okay. So these two orbitals will overlap, and the overlap is along their axis. So this is oxygen, this is iodine. The overlap is along their axis. Now you also see that iodine has two lone pairs. So we can say that those two lone pairs are, for this one, let's say this is this one, and then here, let's say this one. And then iodine will form a bond with the second oxygen, and you see here there's a double bond. So let's explain first the first bond. The first bond is an overlap between these two, which looks like this as well. The second bond, however, to explain that, the overlap cannot occupy this region, and for iodine, this half-filled orbitals is placed in a 5d orbital, and 5d orbitals, one of the 5d orbitals has this particular shape. Okay, so let's say this one, and since it is half-filled, let us just say that this is let us shade the half of the lobes, kind of look like that. And then for oxygen, this one, it's in a p orbital. So we know that p orbitals have dumbbell shapes, and since it is half-filled, so since the first bond, once again, the first bond occurs along their axis, it is head-on. It is a head-on overlap. The second bond between iodine and oxygen cannot occur in this region, and it's gonna be a sideway overlap between these two. These two will overlap. Actually, I can make this drawing bigger to emphasize the overlap. Okay, so sideways, or side, let's just say side overlap. We have a name for the first overlap, which is called a sigma bond, sigma, and then the side overlap is called pi. The symbol is pi bond. For you to understand this further, I encourage you to look at images of different sigma and pi bonds. So here, if this particular assumption is true, then this pi bond overlap is the here an overlap between a d and a p orbital. So once again, first bond is a sigma bond, second bond is a pi bond. Okay, so that is number 2. Number 2 tells us that when covalent bonds occur, there is an overlapping of orbitals. So that's the concept here. For number 3, formation of equivalent orbitals. For our central atom, iodine, in order for iodine to assume a tetrahedral arrangement, it will need to prepare equivalent orbitals. So the number of equivalent orbitals that iodine will have to prepare will be equal to the number of lone pairs it has plus the number of sigma bonds. So here, it will need to prepare 1, 2, 3, 4. Now once again, the number of equivalent orbitals that the central atom will need to prepare will be equal to the number of lone pairs and the number of sigma bonds. So here, if we say that this is just an s orbital, then it will be spherical in shape. And then if this is p orbital, then dumbbell shape. The s orbital actually doesn't make it favorable for iodine to assume a tetrahedral arrangement. So instead of an s orbital, it will make this 4 orbitals equivalent, replace this into equivalent sp3 orbitals. And instead of this one, it will look like okay, so the equivalent orbital will kind of look like this in terms of orientation. Let us say that this orbital here is the one that formed a bond with oxygen number 2. Okay, this one holds the lone pairs, this one also holds the lone pairs. This one bond with oxygen number 1. Okay, here probably for the second oxygen, this one, this is the pi bond, this one is the sigma bond. Let's say this is the overlap to form a sigma bond, and then there's an overlap to form the second bond, the pi bond. Okay, so once again, we're using textbook procedures to explain how bonding occurred. Now let's move on to formal charges. Okay, there's a formula for computing the formal charge, and that is you first consider the group number minus the number of unshared electrons minus the number of shared electrons. And it actually helps you determine the formal charge if you wrote down the structure of the polyatomic ion in this form, because in this form you can actually count the number of unshared electrons and the number of shared electrons. If your structure is written this way, one way to remember the formula for formal charge is first group number of the element minus the number of unshared electrons. For oxygen, 6 electrons are unshared. When you say unshared, it is not used to bond with other atoms. And the common mistake here is instead of writing for this oxygen, instead of writing 6 unshared electrons, the common mistake is writing down 3 because they mistake this for lone pairs. So here, number of dots, and the number of shared electrons for this oxygen, only 1 electron is shared. Number of lines. So just an easy formula to remember, provided you have already made the structure. Okay, for oxygen number 1, oxygen belongs to group 6. 6 number of unshared electrons, 1 shared electron. Total formal charge is -1. For iodine is group number 7. Number of unshared electrons, 1, 2, 3, 4. Number of shared electrons, 1, 2, 3. 0. 0 formal charge. Here, once again, oxygen is in group 6. Number of unshared electrons, 1, 2, 3, 4. Number of shared electrons, 1, 2. 0. If we add the total formal charge for each atoms, it should be equal to the charge of the ion itself. For molecules, the total formal charge should be equal to 0 because molecules are neutral. Sometimes you are asked to write down the formal charge beside the element. So here, -1, or probably without the circle. -1, this one is 0, this one is 0. So there you go, that's the formal charge for each atoms, and the total is equal to the charge of the ion. Okay, so there you go. So those are the steps that you can repeatedly use when you're just given the chemical formula of a molecule or an ion. And with that, I hope this particular procedure that I showed you will help you in dealing with this topic and will help you study, deepen your knowledge regarding this part of chemistry. Okay, and once again, thank you for watching.